very briefly introduce my coworkers, Paul Dagnelie and Dan Kimmel. They have been doing a lot of work on ZFS Send and Receive, and Dan's going to be talking about what ZFS Send and Receive is, why you'd want to be using it, how it works, and then they're going to be talking about some new cool features in Send and Receive. So,
thank you, Matt. All right, so good morning, everyone. As Dan said, my name is Paul Dagnelie. I'm going to be talking to you about ZFS Send. Also presenting with me today is my colleague, Dan Kimmel. So just a sort of a procedural note, we're going to be doing, I know it's listed as 2 separate presentations, but it's going to be sort of one joint presentation. I'll talk first, and then he will talk later. And then at the end, there will be a session where you can ask both of us questions. But if you have, if something doesn't make sense, raise your hand. We'll try to call on you. Sort of an outline of what we're going to be talking about today. What is ZFS Send? Why would you use it in comparison to some of the other tools that exist? And then we're going to talk about how ZFS Send works, starting from the principles that went into its design, and then talking about how those were achieved. We're going to talk about a recent feature in ZFS Send and Receive that was recently integrated to OpenZFS, resumable Send and Receive that Matt Aarons worked on. And then I'm going to talk to you about a feature that I've been working on recently at Delphix called Redacted Send and Receive. And then Dan will talk to you about compressed send that he's been working on at Delphix. So what is ZFS Send? So basically the idea is that ZFS Send is a command line tool that serializes the content of a snapshot. So you do ZFS Send, the name of your snapshot, and then on standard out, it will emit what we call a send stream that is the serialized version of your snapshot. And then you can pass that send stream to ZFS Receive, which will take that serialized version and create a snapshot out of it. And in addition to sending whole snapshots, you can also do incremental differences between snapshots. So if you have a pool with a file system that has 2 snapshots, A and B, and you want to put those on some other system, you can send snapshot A to that other system, and then you can send an incremental from A to B to that other system. And now both both the source and the target will have snapshot A and snapshot B. And this has a lot of possible use cases. One of them is for remote application of data. For disaster recovery purposes, you want your data to be somewhere that isn't just in one place in case something bad happens. Or if you just have a group working in, say, San Francisco and Boston, and you want them to be working with the same data, you can use ZFS Send and Receive to send that data from one site to another efficiently so that they can all be working with the latest data. You can also use ZFS Send and Receive to achieve backup by serializing these snapshots to long-term storage like tape or disk. So why would you use ZFS Send and Receive instead of other tools that allow you to copy data from place to place? So there's a couple of ways in which you can compare tools. One of them is performance. And there's sort of 3 main axes for a tool like this. The first is that you want the tool to be able to use all of the disk bandwidth you have at your disposal. ZFS, we have these pools of storage which give you great read throughput. And it would be good if the tool that you were using allowed you to make use of all of that. The next one is that you want to be able to saturate your network connection. If you have a 10 gig pipe, you want to send as much data over it as you can. And so tools that can better saturate your pipe are better for transferring data, a lot of data. And finally, you want to use, in general, as little CPU as possible to do these things. And ZFS Send and Receive are actually really well tuned for all 3 of these goals. Another sort of axis in which to measure the quality of a tool is how good of a job it does, right? Not just how fast it is. And ZFS Send and Receive are substantially better than a lot of the alternatives. For one thing, if you have a bunch of snapshots and clones, like you tend to if you're using ZFS, and you want to have those all available on your target system, if you were using a tool like rsync or SCP, you'd have to create separate copies of your data to represent each snapshot. And so your storage usage would go way up on the target system. But since ZFS Send and Receive work at the file system layer, you still get all of the block sharing that ZFS has to offer, which is a really nice benefit. In addition, since we're working at the file system layer at a relatively low layer, you don't have to teach. ZFS Send knows about all of the features of your file system. It knows about permissions and owners and sparse files and extents and all of the things that you need to have as part of your file system but that aren't the data. ZFS Send takes care of it without worrying about any of it. So how does ZFS Send work? So in order to talk about this, I'm going to talk about some of the goals that the team had when they were designing ZFS Send. The first goal is that when you're doing a send operation like this, you really want to read in as little data as possible. Any data you read that you don't use is wasted throughput. And so the way that we do that in ZFS Send is by using the block birth time that Kirk talked about to locate which blocks have changed since the snapshots we care about. The next thing is that, as I said before, you want to be able to use all of the available power of your disks. And so ZFS Send does that through prefetching by issuing many IOs in parallel rather than issuing them serially. You want to be insensitive to network latency because if you have a really a high latency network between one side of the country and the other, you still want to be able to send a lot of data across it. And so ZFS Send is designed to be as unidirectional as possible, sending data in only one direction. Finally, you don't want to have to duplicate the work that you put into implementing features in the ZPL just to duplicate them down for ZFS Send. And so by working at a low layer called the Data Management Unit, or DMU, ZFS Send is insensitive to all of that complexity, so it all just works without any further thought. So now I'm going to go sort of in detail about how each of these things were achieved. So if we want to read the minimum number of blocks necessary to send a snapshot, so the first thing we're going to have to do is we're going to have to traverse the snapshot to find all the data in it. We don't want to read any blocks we don't care about. So we will skip any blocks that we haven't modified since the incremental source, which is called the from snapshot. And we detect this using the block birth time. To compare this to other tools, rsync, for example, if you're sending a large tree of files, has to stat every file in the tree in order to figure out whether it's been modified since the last time a send was done. And if you're doing it on something like a VM file or a database, which is record structured, it has to actually checksum every block to compare to see if they've changed on the target system. So that means that if you change 1 byte in your 10 gigabyte data set, you're going to have to scan all of the files, and if there's large files, potentially all of the blocks in those files, just to make sure that this is really the 1 byte that changed. But since we work at the file system layer, we know already this is the only thing, so we can send it without extra work. As sort of a side note, you don't even need the from snapshot to be around. The data in it isn't accessed. All you need to know is the creation transaction group, or checkpoint as Kirk called it. And so this is actually how ZFS bookmarks work. They record that transaction group. So let me sort of walk through what ZFS Send would look like if you were doing an incremental send on this sort of fake data set. So ZFS is a copy on write file system, tree of indirect blocks pointing down to data blocks. And so you start traversing at the top. And so we read in the top indirect block. And the number in these things represents the birth time of that block. And the snapshot we're sending from was created in transaction group 5. So we read in the indirect block. We look at the first block pointer in it. And we see that that block was written in transaction group 3. Because of the copy on write nature of ZFS, we know automatically that everything below that block has not been written since transaction group 3, because otherwise that block would have had to be rewritten. So that means that we can drop that entire half of the tree without having to read any of that data, because we know we don't need to send it. So now we're going to go look at the next block pointer. That one was updated in transaction group 8. So there's data below it that we care about. So we're going to read in the next block. We look at those block pointers. The first one is born in transaction group 8. So we know that there's data there we care about. We read in the next block. We see the next block pointer, transaction group 8. So now we're going to read in the data block and actually send that over the network. So now we've sent the first block of data. We go back up. We see that the next block was updated in transaction group 4. So we don't care about it. So we just never read in the data block. We never issue that read. We traverse back up, see that the next block pointer has a birth time of 6. Traverse down to its children and see, OK, birth time 6, read and send this data block. Birth time 6, read and send this data block. And now we're done. We traverse back up. And if you look at the blocks that are highlighted versus the blocks that are grayed out, the blocks that are highlighted are exactly what's required to send the things that have changed since transaction group 5. So we've read in only the blocks we need. The next goal was to try to use all of the available disk bandwidth, all of the power that ZFS gives us. When I described sort of what the send looks like on this slide, it was a very serial operation, right? You look at the block pointer, you figure out what to do, then you either issue the read or don't. But if you do that, then you're bound by the latency of your disks rather than the bandwidth or the throughput, and that's not a good state to be in, especially if you're using spinning hard drives. So to get good performance, ZFS Send is designed to use prefetching. When you start a ZFS Send, it creates multiple threads, one of which is the prefetch thread. And it will issue reads for the data blocks that the main thread is going to need, but it doesn't actually wait for the blocks to be read in. It just keeps going and issuing new reads. So that way the main thread will always have the data it needs to send over the network ready for it, is the goal. To prevent it from sort of running away and filling up all your memory with pages, there's a tunable called ZFS Send Q-length that caps how far ahead of you it can get. The next goal is that we want to be insensitive to network latency. And the way that we do this is that ZFS Send just emits data on standard out. It never reads in data. And so you determine what send stream you need to create through the parameters to ZFS Send. They contain things like the most recent snapshot that the two systems have in common, which is the from snap, and the features that the receiving system supports, like embedded blocks or large blocks or compression. And because all of this state is given to you on the command line, you never need a message back from the receiving system except for TCP ACKs and stuff like that, which means that you can be insensitive to network latency. You don't have to have any sort of communication. It also allows you to use it in cases where the receiving system can't answer, for example, backups. You write this send stream to disk, and then you can replay it later. And so the fact that there's no communication involved means that you can use it for this new use case. You can also have more flexible distribution options. I can give the send stream to another system that will deliver it to a bunch of other systems rather than having to send it to them all myself, because we don't have to talk to each other. I just know that these are the contents it needs to contain. Finally, the insensitivity to the complexity at higher layers. At the DMU or data management unit layer, which is where ZFS Send operates, there are no files or directories or metadata objects. Everything is just an object. And so we don't try to interpret what they mean or what they contain. We just send their contents. And then we let the ZPL or POSIX layer on the far side interpret all that complexity and interpret all those features, which means that everything, all the esoteric features that have been added or might be added in the future just work with ZFS Send. Windows users, NFS4 ACLs, sparse files stay sparse when you send them. All of that just works. So now I'm going to talk about a feature that anybody who's used Send and Receive extensively has run into, that they've wanted fixed, that Matt has fixed for us at Delphix, and has been integrated upstream into OpenZFS. So the problem is that a failed ZFS receive, you have to restart. And that can happen if the network goes down or if either of the systems involved reboots, or if there's corruption. If any of that happens, you have to delete the partially received data set and start over from the beginning. And we had a real customer issue where they had a very large database and a fairly small pipe, and it took them 10 days to send the data from one system to another. But the network would go down once a week. And so that sort of leaves you in a bit of a sticky situation. So the solution is resumable ZFS Send and Receive. And so the idea is that when the receive fails, you store some extra state on disk, and you don't delete all the stuff you already got. On disk, you store, in addition to leaving everything around, you store the last object you were successfully receiving and the last offset within that object that you successfully received. And the sender can use that information to resume from where it left off. It skips directly to that point and doesn't reread any of the previous data. But we still want ZFS Send and Receive to be unidirectional, right? We don't want to have this communication process back and forth where they negotiate where to start from. So the idea is that a failed receive will set a property on the file system called the receive resume token, which is this opaque blob of ASCII text that encodes the object to resume from, the offset, as well as a few other pieces of information necessary to recreate the send stream. And then the sysadmin or application using ZFS Send is responsible for getting that information back to the sending side, whether that's copy-pasting it from one window to another, sending it an email, telling it someone over the telephone, however you need to get it done. So this is what it looks like to be used. So we do ZFS Send, and we pipe it to ZFS Receive with this new -s flag. -s means save the state on failure. If the receive fails, you get the receive resume token, and then pass it to ZFS Send with ZFS Send -t, and all it takes is the token. And the token has all of the information necessary to recreate the stream, what snapshot you were sending, what you were sending from, where to resume from, and what features you had enabled. And then you can also abort the receive if you decide you don't need it anymore, and it'll discard the partially received data set and unset the property. And you can also, of course, do this through libzfs in addition to just through the command line. Yes, you can resume. You can make a receive that you are resuming a resumable receive. That still works. Good question. So if you want to see the contents of the resume token, here's an example: ZFS Send -v for verbose and -t and the beginning, of a token, and you can see that it contains the GUID of the snapshot you're sending from, the object and offset to resume from, how far along the stream has gotten, and then the GUID and name of the snapshot you're actually sending. So that's all of the information that you need in order to recreate the send stream. And then if you look at the actual contents of the stream using the Z Stream Dump tool, which lets you look at ZFS Send streams, you can see that the stream will say, okay, we are resuming from this object and offset, and then the first object we send is that object, and the first offset within that object is that offset. So we've skipped past everything that the receiving system already has and started exactly where we need to. So now I'm going to talk to you about a feature that I've been working on recently at Delphix called Redacted Send and Receive, and then Dan's going to talk to you about Compressed Send and Receive. So what is Redacted Send and Receive? So let's say you have a big database or a big set of files, and they contain sensitive information like social security numbers or credit card information or medical records that you can't just send to whatever system you want. But you want to give this to your developers or analysts somewhere else outside of your production zone. So one way you could do this with ZFS is that you could make a clone, cover up all of the secret or restricted information with other stuff, and then send that. But if you do that using ZFS Send, if you want the block sharing, you still have to send the parent because you can't send the clones and have them be related to each other without sending the parent. Or you have to use a tool like rsync or something like that, but then you're not getting the other benefits that ZFS Send provides. So the solution is Redacted Send and Receive. The idea is that the clones, you've said that they're going to modify all of this secret or sensitive information. So any data that the clones don't reference, you don't send. And so it'll leave you with a partially intact main file system. And then each of the clones will still have all of their data in them. And so you get the space savings, you don't send the information, and you get all the other benefits that ZFS Send has to offer. So let me sort of give an analogy or an example of what this would look like. This is a picture from the party where they were open sourcing ZFS. You can see that they're getting ready to party in fine style. So let's say you have a database that has a bunch of pictures like this, and for whatever reason, you can't send people's faces to the your target system. So you make a clone of your database and replace them all with a different face. So now you have your file system and your clone, and then you want to do a redacted send. So your main file system, when you do the redacted send, it'll look at the clone and look at the main file system. It'll say, okay, the only thing that's changed are these parts here. So we don't send those parts when we're doing the redacted send. So on the far side, you end up with something that looks like this. And then the incremental from the normal image to the clone, it works exactly the same way as normal. It sees the only things that have changed are the faces, so that's what it sends. And now you have on the far side all of the information necessary to recreate your masked image without having to send the faces that you weren't allowed to send over the network. So the way that it works sort of more technically is you're traversing the metadata of the various clones while you're traversing the snapshot that you're sending. You find the ranges that the clones have changed. You find the intersections of all of those ranges to find the things that every clone has modified, because those are the things you think are sensitive. And then you don't, any blocks that the ToSnap would send in those ranges, you simply don't send. And then you store that list of blocks you didn't send in a new kind of bookmark we call a redaction bookmark that you'll use for incremental sends. Now, I could give probably like an hour-long talk on how redacted send and receive works because it's a huge change. It's over 5,000 lines of code. But to give you sort of a taste of what it looks like, this is the block diagram of how data flows in redacted send and receive. Each box is a thread, each arrow is a queue. To give you a sense of scale, everything green is new in redacted send and receive. So where there were once 3 threads, there are now 6 plus end threads. And this isn't including any of the changes to receive or any of the other code that helps this work. So ZFS Redacted Send and Receive was integrated last Friday, 3 days ago. We hope to have the code published January, February next year. And we hope to have it upstreamed into the Open ZFS repository, I guess, in summer of 2016. If you want some of those nitty-gritty technical details that I was talking about, I'm going to be doing a blog post about the implementation of it on my Delphix blog. And of course, I'll be here today and tomorrow, and you can ask me about it, or you can ask me offline by email or on Freenode on the IRC channel. And so now Dan is going to talk to you about compressed send and receive.
Hey guys, can you hear me okay? All right, perfect. So like like Paul said, I'm Dan. Nice to meet you. This is my first OpenZFS conference, so I'm really excited to be here. Compress Send Receive was sort of envisioned to solve the problem where you're sending data from one file system on, let's say, your West Coast data center to the file system on your East Coast data center. This is a very common problem that you run into with ZFS Send Receive, where you're trying to move a lot of data over a relatively small pipe. I added the -v flag here so that we can sort of see the output as it's sending. The first thing it prints out is the estimated send size, 35 gigabytes. Yeah, that's about right. I remember writing 35 gigs into this file system. So then a couple of seconds later, we see that it's sending, and it's really, really slow. Only 200 kilobytes a second. So we're going to be sitting here for a little while. Here we are a couple of seconds later at the 1 meg mark, and I'm basically Googling 35,000 times 4 seconds converted into days. And when I see the result of that, basically I realize that I'm this cat watching paint dry, and I'm going to be here for a long time waiting for this to finish. So Send Receive right now is basically sending all of your data uncompressed. And so what you might do as sort of an initial step to make this a little bit better is to compress the data before it's sent over the internet and unzip it on the other side. So what we would do here is basically read the data from ZFS using ZFS Send, run it through gzip, send it over the network, but less data this time because we've basically compressed it down to some smaller size, and then decompress it on the other side and receive it into the new file system. So there's a couple of problems with this approach. First, gzip is just really slow. As most ZFS users know, maybe we could switch to using something like LZ4 to get a faster compression speed. Next up is gzip is single-threaded, and it will completely peg one CPU while it's running. So we'll basically be bound by that CPU's throughput. What you could do to sort of solve this problem is like chunk up your data stream and gzip each one in parallel, and basically peg all your CPUs. But the third problem is that the other CPUs aren't idle on this system as the solution is laid out already. The problem is really that ZFS is already storing your data compressed in the file system if you have that enabled. And so rather than just taking it uncompressed, compressing it as it goes through gzip and sending it, what you're really doing is you're reading it from disk where it's already compressed. ZFS decompresses it to create the send stream. You're recompressing it with gzip, sending data over the network, decompressing it, receiving it, and recompressing it as it's written down to disk. So that's a lot of overhead for what we're trying to do, which is basically just send less data over the network. So the solution for this problem is essentially trying to cancel out these decompress, compress loops on each side of the wire. I'm basically going to describe this as if it's reading data from disk always, but know that this actually depends on George Wilson's compressed arc work, which he'll be talking about today after lunch. So the idea here is basically we read the data from disk where it's already compressed. We send less data over the network, just leave it in its compressed format, and then we receive the stream in its compressed format directly onto the disks in the receiving system. So the way that it actually works on the command line is basically very simple. You just add the -c flag to the send command, and now you can see that the estimated send size is much smaller, only 10 gigs. So we're basically going to save hours to days of that original send. As I mentioned before, this is actually not doing any compression on the fly. This is just using the compression that has already taken place. So whatever compression algorithm you used to write your data into the Z pool to begin with, or into your file system to begin with, that's the compression algorithm that will be used to send the data over. So what this allows us to do is not bottleneck on CPU on either compression or decompression, and it'll still save us compress ratio. There will be a multiplier of compress ratio in the amount of logical data that we can send per network physical throughput. So in order to make this change, Paul already introduced the stream dump, which shows you what an actual send stream looks like, sort of in human readable format. Basically, we changed a couple of fields or changed a field from sort of normal uncompressed length to logical size, and we added 2 new fields: compression type, which just tells it the file system, what was the actual compression type that was in use. In this case, 15 represents LZ4, and the compressed size, so the amount of data that we're actually sending over the wire. And you can see that for these two example write records in the send stream, we actually have a pretty significant compressed ratio for these two records. So the results of this in our sort of in-lab performance testing are that the compression ratio of like around 2.5 results in a speedup of around 2.5 when you're restricted on the network throughput. And when you're sending the data from a completely cached data set with no network, so basically piping the results of the send stream into dev null, for instance, you see a really big reduction in CPU costs for a full ZFS send. And this CPU cost number is actually deceptively similar to the compression ratio. They're actually not related. The compression ratio, or sorry, excuse me, the CPU cost here is basically the ratio between cost of decompressing plus sending divided by cost of sending, and there's no compression ratio involved in that. So in terms of the sort of time frame for this, well, it says about to integrate at Delphix, but I just integrated it yesterday. We're expecting to publish this in the same release that Redacted Send Receive will be going out, so probably January 2016. And our estimated upstream date is probably around summer 2016. And again, it sort of depends on having George's work on the compressed arc come in before it. So with that, we'd like to open it up to any questions that you guys have. Yeah, so for compressed send, when you have compression, a new compression algorithm that's added on the sender, but it hasn't been added on the receiver, right? So basically, in order to add the new compression algorithm, you would add a new flag to the file system that's being sent, and the receiving side would recognize that it didn't have that compression algorithm implemented, and it would reject the stream. So you would need to have basically similar versions of ZFS running on both ends. If it's not compressed on the sending side, then you're better off just using gzip. Doesn't give you any benefit there. Yeah. Yeah, so we actually decided not to send the metadata compressed simply to make byte swapping for if you were sending from like an x86 system to a Spark system simpler, so that the Spark system wouldn't have to byte swap a compressed stream as it's ingesting it. Well, I mean, part of the design of ZFS Send Receive is that there is no negotiation. We could, I don't know, I mean.
So, I mean, you'd have to implement a negotiation phase, which would involve back and forth communication, which would involve changing the interface to ZFS Send. So you'd basically be rewriting all of ZFS Send to add a way for there to be communication at all. So you could add another flag for it, I guess, would be the other way to do it. But I think that was something we didn't feel was important, and someone else could certainly do if they decided they wanted it.
Yeah.
So actually, as part of the resumable send receive work, there is now a checksum in every record of ZFS send streams, which means that if you're using a resumable receive and it detects that a particular record is corrupted, it can resume from that point rather than having to start from the beginning or get all the way to the end and detect the corruption has happened. Malicious corruption. I don't know that there is a good way to prevent, like you can always craft a send stream that will be accepted by the other system that wasn't, generated by ZFS Send. Yeah, basically. There does need to be some hardening of ZFS Receive, and I think we actually have a hackathon project that's called Make ZFS Receive Less Trusting.
What was the thought process around making line assist
I believe that Matt could speak better to this, but I suspect that the answer was that if you weren't going to be doing a resumable receive, you didn't want to accidentally leave all that data lying around where, it would just keep eating up space until you remembered that you'd done it and abort the receive. Are there any other questions? Cool. Well, thank you all for your time.